we're going to get started on another one of the selected topics that I said we're going to cover. This is going to be over section 11.3, and in this section we're going to be discussing Merssene Primes. We have seen what Merssene Primes are and Merssene numbers actually in general in section 11.2 when we discussed perfect, even perfect numbers. So in this section, it is natural to actually go and take a more extensive look at the the numbers that are actually we use to generate even perfect numbers, and these are the Merssene primes. So the objectives first, we're going to define what Merssene numbers are, and then in particular what are Merssene primes. Then we're going to look at the prime factors of the Merssene numbers, and also at some special types of Merssene numbers. Then we're going to end with looking at Euler's theorem on all perfect numbers. Even though, as we're going to see, there is no all perfect numbers are known, but we're going to give a condition if to look for all perfect numbers, what kind of condition they must satisfy. All right. So let's start with the definition. So here it is. Let n be a positive integer. The nth Merssene prime, Merssene number, sorry, is this. We denote it by m sub n, and it's equal to the n minus 1. Now, a Merssene prime, on the other hand, in order to define it, let's recall that if m sub n is a prime, then n must be a prime. So in other words, if the Merssene number is actually itself is a prime, then the exponent is a prime. However, the purpose of this statement is not the truth. This means that is if n equal b is a prime, then m sub p is equal to the p minus 1 need not be a prime. In other words, this could be composite. Need not be a prime. For example, if you look at M11 is equal to the 11 minus 1, this is composite. Actually, this is product of 23 multiplied by 89. All right. So for this reason, the way we're going to define a Merssene prime is a number that is, first of all, I want it to be a prime, all right? means the exponent needs to be a prime, and the number itself is a prime. So a Merssene prime is a number of this form, m sub p equal q to the p minus 1, where p is a prime, and m sub p is a prime. In other words, there are two conditions that need to be satisfied: the exponent, or the where, of course, p is in all of this, p is a prime. All right, so this is the type of number that we're going to be interested in. Now, Merssene Primes has a very long history, and I encourage you, would like you to actually read the history of Merssene, that is in section 11.1, and also the some of the history on page 228. All right, so please read that. Uh, 228. This is the story of Frank Nelson Cole, and his paper, or his discovery of M67 is composite. I hope it will inspire you when you are working on the problems, and to see, the amount of time Frank Nelson actually spent on proving or finding a prime factorization of M67. You're going to find this is inspirational, I hope. All right? So I'm going to leave that for you. I don't want to say very much about it, except just something is interesting. All right? So let's get started by looking at some special types of Merssene numbers. And find some sort of prime factorization of such numbers. So this is the first theorem. Theorem 11.3. If P and Q, which is of the form 2P plus 1, are primes, then either both of these are primes, okay? Then either Q divides M sub P, or Q divides M sub P plus 2, but not both. So in other words, this theorem tells us that, of course, if the first condition is satisfied, then M sub P is composite for sure, all right? But if this does not divide, Q does not divide M sub P, means it's going to divide this one. We don't know, of course, if there's another prime would divide. So it won't be a primality testing for Merssene primes, but at least it would rule out some of those Merssene primes to be actually composite. All right. The proof of this is very straightforward. Of course, since Q is odd, this implies Q and the Q are relatively prime. Then we can apply Fermat's theorem. We would have 2 to the power the Q minus 1 is congruent to 1 mod Q. And let's write this one in terms of the P. So this is if and only if 2P. So this is going to be 2P. All right, plus 2 minus 1. So it's 2P is congruent to 1 mod Q. And this implies the Q divides 2 to the 2P minus 1, which we can write as a difference of 2 squared, 2 to the P minus 1, 2 to the P plus 1. And since the Q is a prime, it's going to divide one of these, either the first or the second, and this happens to be just the actually, that implies Q divides with the P minus 1, which is actually M sub P, or Q divides 2 to the P plus 1, which is M sub P plus 2. All right. Now, it doesn't divide both. Okay, Q. Assume Q does divide both, then we're gonna, this was going to lead to a contradiction. Assume that Q divides MP and Q divides M sub P plus 2. So this implies that Q divides a combination of these, which is the first one minus the second, and this is equal to 2, which leads to a contradiction, because this means that the Q divides Q, contradiction because the Q is off, right? All right. Let's consider an example how we can show using this theorem a certain Merssene number is composite, in fact, with the exponent being a prime. Remember, in order for it to be a Merssene prime, it must be, the exponent must be a prime and the resulting number is a prime. So in order to check for Merssene prime, we need to look at only those with prime exponents, but not everyone give us a Merssene prime. So here's an example. Let's take P equal to 23, Q equal to 23 plus 1. This is 47. And the question is, you need to check, does 47 divides MP or 47 divides MP plus? So it's gonna, one of these, divisibility is gonna actually hold, all right? Either this or the other one. And to do this, this means I wanted to look at the M23. This is going to be 2, 23 minus 1. So I would like to look at what is, this is mod 47, okay? So 2, 23, and we could use, all kinds of tricks. One very straightforward is to write this as sum, as 23 as sums of powers of 2, all right? And this is actually equal to 16 plus 4 plus 2 plus 4. And we can use fast exponentiation to calculate each one of these. And if you do, you're going to see that 2 to the 16 is going to be congruent to actually 18 mod 47. So we're going to do more mod 47. And again, remember when we do this one, we take 2 squared and 2 to the 4, just we keep squared. And 2 to the 4 is congruent to 16. And 2 squared is 4. And 2 to the 1 is 2. When you multiply these and actually keep it even reducing mod 47, you're going to see this is congruent to 48 and or congruent to 1 mod 47. So yes, this means that actually this one is 48, okay? And when you take 23 minus 1, this becomes congruent to 0 mod 47. Okay, so this means that 47 divides M sub P, so M23 is, this one is composite. You don't need to go any further, so this is a composite number. All right, now we will be interested in determining, under what conditions the Q would be actually divisible by M sub P or divisible by M sub P plus 2. In other words, are there extra conditions that we can impose on a Q to come with divisibility of one, not the other? And this is actually the next theorem, and even it's a little more general than this. It doesn't have to have the form that the Merssene Primes is M sub P. So here's theorem 11.4. Okay, so this is, we're going to put some extra condition on the Q to ensure that it will be divisible by M sub P or M sub P plus 2. So it says this: if the Q is like this is a prime. So in other words, the engineer does not need to be a prime. So of course, when it is a prime, then this becomes exactly the type of number it's mentioned in the previous theorem. Okay. Then the following is true: A. If the Q divides M sub N, then the Q is congruent to 1 mod 8, or the Q is congruent to 7 mod 8. So these are the type of prime factors that actually will be. And on the other hand, if the Q divides M sub N plus 2, then the Q is congruent to 3 mod 8, or the Q is congruent to 5 mod 8. All right. Now, this together with the previous term. So if Q is of the form 2p plus 1, all right, where p is a prime, then we know that one of these is going to happen. So if I have this extra information, then we know which one of these will be, all right? All right, so let's go ahead and do the proof in here. Let's see that, let's go with A. Q divides Mn means we have a Q divides 2 to the n minus 1. And this is equivalent to saying, or this is equal to, rather, 2 to the power Q minus 1 over 2 minus 1. Remember, because here, since Q is equal to n plus 1, this implies n is equal to Q minus 1 over. And this in itself, all right, is equivalent to saying that 2 to the power Q minus 1 over 2 minus 1 is congruent to 0 mod PQ. And also this is equivalent to saying that 2 Q minus 1 over 2 is congruent to 1 mod Q. And as well as actually this is congruent also to 2 to the power n. Yeah, that's one. That's all right. Mod Q. And this means that 2, the Legendre simple 2 pi Q is equal to 1. Then we're going to apply Theorem 9.6, which tells us when this 2 is actually a quadratic residue. This says that 2 by 9, by Q, sorry, not 9, is equal to 1, holds if the Q is congruent to 1 mod 8, or the Q is congruent to 7 mod. All right. Similarly, we go with the other argument. Second part, B, if Q divides MP plus Mn, sorry, P plus 2. This is again equivalent to Q divides 2 to the power Q minus 1 over 2 plus 2. Actually, this is plus 1. Because M is minus 1 plus 2, and this is equivalent to Q divides 2 to the Q minus 1 over 2 plus 1. And again, this makes this congruence 2 to the Q minus 1 over 2 Q is congruent to negative 1 mod Q, and it makes the Q by Q, in this case, is negative 1, and again by theorem 9.6, this happens if the Q congruent to 3 mod 8, or Q is congruent to 5 mod 8. All right? Okay. Now let's apply this to the case in the previous theorem. As I said, it would give us a way to determine that a certain Merssene number is composite. So it's compositeness test, basically. Yeah, we're going to state this is in a form of a corollary. And if P and Q equal to P plus 1 are primes, with P is congruent to 3 mod 4, then Q would divide M sub P, hence M sub P is composite. All right. Here's the proof. Now we know that P is an odd prime, and this makes that P either of the 4K plus 1 is congruent to 1 mod 4, or P of the form 4K plus 6. Now, if the Q is actually if the Q, or since the Q is equal to this, now Q is equal to P plus 1. Now, since we are saying that P is of this form, all right, and P is of the form is actually equal to 4K plus 3, then Q is going to be 8, 2 times 4K plus 3 plus 1, and this is going to be 8K plus 7. So this is the form of the Q, and then by first of all theorem 11.4, we have Q divides we have, by this theorem, we have Q either divides, okay, MP, or Q divides MP plus 2, right? Now let's see if what happens if let me actually just double check something. All right, so we have this. Actually, this is the previous theorem. This is 11.3. 11.3. All right. Now, since we have actually Q of this form, then theorem 11.4, it says that since the Q is of the form 8k plus 7, this implies actually Q divides the first one, M sub P, not the other one, because it cannot divide both. Now, so this takes care of one form of the primes. Now let's look at the other one. Let's assume P is of the form 4k plus 1. Now, if P is equal 4k plus 1, this implies Q is going to be of the form 2, 4k plus 1, and this becomes 4k plus 6. All right? And so in this case, if we have actually 8. All right? So we have this one. Similarly, we're going to have this. We know that again, if you divide either MP or if you divide MP plus 2. All right? Now, if it happens that if the Q divides MP, then the Q is going to divide the sum of these, linear combination, which is equal to 2, and this would be a contradiction, all right? So in other words, from these two choices, this implies that the Q does not divide MP, but the Q divides MP plus. All right? So for this reason, the only case where we have a prime factor, which is the Q, is when P satisfies this condition. All right. Now, in the next theorem, we're going to look at the, in general, what type of prime factors a Merssene composite number may have. All right? So in some sense, this applies to a special type of Merssene numbers, okay, that are the form where P and Q is mentioned in here. Next one is more general, all right? And actually, this is theorem 11.5. And this is the statement of this theorem. It says that if P is an order prime, of course, the case where P is equal to 2, we are not even discussing that. Even in the previous theorem, we are assuming implicitly that P is an odd prime, okay? Because for P is equal to 2, the Merssene Primes is 3, and it is, of course, it is a prime. So no big deal. All right? Then any prime factor of M sub P is of this form. 2kp plus 1 for some k bigger than or equal to 0. All right. So any prime factor of a Merssene number, general Merssene number, with, well, for when these are prime, because we are interested in those, they are composite, basically. All right, it says it must be of this form. All right, so let's assume that let the Q be an odd prime factor of M sub p. This implies, of course, M sub p is going to be congruent to 0 mod Q. And this is the same as saying 2 to the power, actually p is congruent to 1 mod Q. Now we're going to look at the order. Let's look at the order of 2 mod Q. And let's call this is K. So then we have, of course, 2 to the K is congruent to 1 mod Q. Actually, let me rename there. Let me call it, this is L. K, I'm using it for something else. All right? So this is L. All right? We have the following, is it true? Since these two congruences implies that the L must divide P. L must divide P. All right? Because the order is the smallest. All right? Also, we have L cannot equal to 1, all right? It must be bigger than 1, since 2 to the 1 is not congruent to 1 mod Q. All right? Because we are assuming Q is a prime factor, all right? So what does this mean? This means that the L must be bigger than or equal to 1, since L divides P, so it means that actually L is equal to P. All right? So we have this conclusion. From all of this, we conclude that L is equal to P. All right, let's look at a different scenario. We have 2Q, the greatest common divisor of these is equal to 1 by Fermat's theorem. We have another congruence, and this, which is 2 to the power Q minus 1 is congruent to 1 mod Q. And this again in itself implies that the L or the P, L which is equal to P, also divides the Q minus 1. Because the exponent that makes 2 goes to 1. And this implies Q minus 1 is equal to KP for some integer k. So let me call this is T. Let me call this is T. So at the end, I'm going to end up with K. T for some integer k. T. All right. so let's see this one. So we have this one. Now, if Q is odd, implies Q minus 1 is even. And since P is odd, the T must be even. So this implies T must be even. Let's say P equals 2K. And all together now, so therefore we have a Q minus 1 is equal to 2KP, and this makes Q, this prime divisor is 2KP plus 1. All right. This is quite important and useful in ruling out certain Merssene or candidate for Merssene primes, means the M sub P, to be actually composite. Okay, so it's a compositeness test for such M sub P. And here's an example to show how we would use this theorem. It's up like this. Like the or theorem 11.5 to M7. Now we're going to actually show it is composite. Let's say it will not be a primality test, but it can rule out this is being a composite. So here it is. We want to look at so prime factors if M sub 17 is composite. Its prime factors by the theorem, right, has this form, R of the form 2K multiplied by 17 plus 1, or 34K plus 1. Also we also know if, again, M17 is composite, it has a prime factor less than or equal to the square root of M17. All right? Now, the square root of M17, this is approximately equal to 362. So in other words, to determine or show that M17 is composite, or it would waste our time if we don't find a prime factor actually divides M17 and less than or equal to this number, then we don't know. Means the test will fail. So the idea here is to consider primes of this form. So we're going to consider primes of the form 34K plus 1 and less than or equal to 360. I cannot be equal, that's an even, but at least less than. All right? And it's a matter of calculating these values. All right? So this form for, let me put a table in here. I'm not going to go and fill all the table out completely. is the table. So this is K, and this is 34K plus 1. And this one is this prime composite. We only want to look at the prime that we get out of here. So it looks like we're going to go 1, 2, 3, up to the last number that exceeds 362 is 11. All right, this one is 35. This is not the prime. You don't need to worry about it. 2 is not a prime. Okay. 3, yes, this one is a prime. It gives us 103. So this is a prime. And it doesn't divide. You can check that this one does not divide 17. Then other primes comes in with 137. Again, this is a prime. And it doesn't divide. There are 2 more primes that actually comes out of this. This is 239, all right, and 273. And also a 307. And all of these are primes. And none of them actually divides. Actually, this proves it is a prime, sorry. It is a part because none of these actually, as I said, it's composite. So none of I made actually I stated it incorrectly. Okay, actually this proves that M17 is a prime because none of these actually does divide. Okay, 239 and 273 and the 307. All of these does not divide M17. So in other words, M17 does not have any prime factor. Okay, because if it has a prime factor, it must be of this form. I'm sorry. All right. Now we're going to actually do a little better by eliminating some of the cases in here. Means next year it gives us more restrictions on the prime in this case there are more restriction on Q, all right, to make it actually be a prime factor. All right, so this is the 11.6. Please like this again. If P is an odd prime, then any prime factor or divisor, the Q of M sub P is of this form. Q need to be congruent to plus or minus 1 mod A. In other words, we don't need to consider the list of primes that we have before. We can eliminate anyone that is not of this form. All right. Now this tends out to be, for larger Merssene numbers, it is helpful. All right. For the example which we just worked out, it's going to eliminate one actually of the prime candidates. All right, let's look at the proof of this. So we have M P, of course, since we have a prime factor. So let Q be a prime factor of M sub P. This implies a Q divide. Or this statement could be ambiguous, means there is no prime, all right? So this implies that, and this. In other words, here, the way it is stated in any prime factor, so we're kind of assuming this one has a prime factor. If it doesn't have, then it's going to be a prime, M something. All right, so this means that the 2 to the power P is congruent to 1 mod PQ. All right, now we have by previous theorem, 11.5, we know that the Q is of this form. For some, okay. Now let's apply Euler's criterion. Of course, 2 and the Q are relatively prime, so we can take this and actually let me apply Euler's criterion in the form of Legendre symbol. Okay, so this one is going to be congruent to 2 to the power Q minus 1 over 2 mod Q. And see what that Q minus 1 over 2 will be. And that all together implies that from here we have the Q minus 1 over 2 is equal KP. Okay, so we're going to be using this. Implies 2 to the power K P. This one is, and this is the Legendre symbol also. Okay, so this is 2 over Q congruent to this. And this is same as this. And we have this one to the K. And we have also 2 to the P is congruent to 1 mod the Q. Mod the Q. And this makes 2 to the Q is equal 1. All right. Now, with this being 1, then when do we get 1 for the Legendre symbol with 2? It must be congruent to 1 or 7, actually, which we could write this by Theorem 9.6. Q must be congruent to 1 mod 8, or Q is congruent to 7 mod 8. And the Q congruent to 1 mod 8 is equivalent to negative 1 mod 8. So these are equivalent things. All right. Now, again, as I said, if you look at the previous example, okay, in the previous example where we have M17, and we found out that the primes, which are less than or equal the square root of M17, which is the 362, are this: 103, 137, 239, and 307. Which we check each one of these and find that none of these is divisible by M17. This number is not of this form. The form congruent to plus minus 1 mod A. So we can eliminate this. As I said, for larger Merssene numbers, we might actually have more than one prime to be not considered, okay? But here only one. All right, the last part of this lecture is concerning odd perfect numbers. The proof I'm going to present it's pretty much the same as the one in the book, except it's done in a slightly different way. I hope it looks more transparent. And as I mentioned, and I'll mention again, that there is no known odd perfect number. So it's your chance to discover one and make a name for yourself. All right? However, we're going to prove a theorem which tells us, if someone to search for an odd perfect prime, what they need type of numbers to consider. Okay? And this is the last theorem, 11.7. This theorem was stated and proved by Euler. All right, and it reads the following: if n is an odd perfect number, then the prime factorization of n is going to look like this: P1, K1, where P1 is actually an odd prime raised to an odd exponent. Okay, K1. Then all other primes is going to appear with an even exponent to J1, P3, 2, J3. Think of it, this is J1, this is 2, and so on. And this is R2, J1. Where the p's of i's are odd, distinct primes, and P1, the first one, is congruent to 1 mod 4, and the exponent of that prime is also congruent to 1 mod 4. Okay? So special prime factorization for odd perfect numbers. Okay? It's an odd prime of a special form. The exponent is also odd. Okay? One odd exponent, and all others are even. All right? And we don't care about the other types of primes. All right? The proof of this is actually centered on looking at, because n is a perfect number, so we're going to have sigma of n is equal to 2n. So we're going to look, analyze, divisibility with sigma of n, which is twice n. Now, remember n is also as an R, right? Okay. Well, first I want to start with a lemma, kind of to break the longer proof into two pieces. And in the first, in this lemma, we're going to show the existence of an odd prime, okay? With there is one of the prime factors, basically. One of the prime factors must appear to the first exponent, to an odd exponent, okay? To an odd exponent. And then we're going to, in the proof of the theorem, show what type of a prime and K1 it will be. All right? So here's the first lemma. And it says that if n is a perfect odd number, then n must have exactly one prime of an odd power in the prime factorization of n. In the prime factorization of n. All right? Here we go. Of course, we're going to prove this one by contradiction. So we're going to assume that there is no odd power, okay? So we're going to consider two cases. Case one, no odd power. This is equivalent to all powers are all powers of p sub I are even. In the second case, there is more than one odd one. Okay, because we say that exactly. So either none, this is one, and no. All right, let's take n. It says P1, H1, P2, H2, P sub R, H sub R, where H sub I are sorry, even. All these are even. All between 1 and. All right. Let's look at sigma. We know that, and these are, of course, all distinct. Of course, these are the prime factorization, and these are distinct. Are distinct odd prime, because this n is odd. So you don't need to look at sigma of one of them. You use it to gain some information about sigma of n. Now we know that sigma, the sum of divisors of pi hi is equal 1 plus p sub I square p sub I plus h. So this is hi plus 1, and this is r. because each an is even, and this is odd for everyone up to r. And this implies that sigma of n is going to be the product of all of these so it's multiplicative, and this becomes, of course, a product of odd. So this becomes h1 plus 1, h2 plus 1, h1 plus 1. This is 1. Well, that's going to contradict, but we know that sigma of 2n is equal to n. But sigma of n is equal to n. This implies contradiction. All right, let's look at the case 2. Now we know that we cannot have all the powers are even. Let's assume it has at least 2. So assume that there are at least 2 odd export. It say is this the p sub I, h sub I, and p sub j, h sub j, where the hi and hj are odd. And I'm going to show that this is not possible. All right? We're going to have more, and this argument actually works if we have more than 2. All right? 2 or more, basically. And again, let's look at the sigma of these. So sigma of pi hi. This is as before, hi plus 1. And since we have hi is odd, this means this one is even. And also we have sigma of p sub j, h sub j. This one is also even. And now when we look at the sigma of n, we're going to find it's a multiple of 4. All right? So sigma sub n, when we write it, we take this one out. So we're going to take these 2. P sub j, h sub j. Then the product of, let's say k does not equal I or j of the remaining ones. K, h sub j. Okay. So this is going to be 4 times something. Okay. So, let me say it's a multiple of 4. So this is multiple of 4. And let me actually write it as 4L. This is because this one is even, this one is even, so we have 2 and 2 there. So this becomes 4L for some integer L. Well, this means that 4 divides sigma of n. Well, sigma of n is equal to n. So this implies 2 divides n. And this is a contradiction because n is, since n is odd. And this take care of course, if there are others, as you can see, it's going to be, more even numbers going to be all multiplied out, and it will lead to a contradiction in a similar way. Actually, we just can take 4 of them and it leads to a contradiction. All right, now we are ready to present the proof of Euler's theorem. Actually, most of the work is done in this lemma. All we have to do is this. So this is the conclusion which we have in here, that we only, n. So here's the proof of Euler's theorem. One of Euler's theorem. Many Euler's theorems we studied this semester. All right, now we know that n must have this. 2J2 of BR2. This is from the lemma. So we know that this is what n should look like, where all what we know so far, where P1 is odd prime, and K1 is odd integer. So what we need to show? We need to show that two things. P1 is congruent to 1 mod 4, and K1 also is congruent to 1 mod 4. So now, since we have actually P1 is an odd prime and K1 is also an odd integer, we only need to show that neither one of these, so this is equivalent to show neither P1 is congruent to 3 mod 4, this last prime, and the other case, or actually ignore the other case. We cannot have both of these. Actually, K1 is not congruent to 3 mod. All right. So again, let's look at sigma of these, and in other words, we have to do it by contradiction again. All right. So let's look at assume that. We're going to do it one at a time. Assume that P1 is congruent to 3 mod 4. All right. So let's look at the sigma of P1 to the K1. All right. So this is, of course, is equal P1 K1 plus P2 K1 minus 1. Sorry, 1 plus P1 plus 1. I'm going to be factoring out of this P1 plus 1. And you can check this by direct multiplication that actually this is the correct factoring. In here, we're going to take P1K minus 1, then P1K 1 minus 3. So we're going to take, actually subtract the odd number. Then we have P1, K1 minus 5, and so on. Up to P1 to the 1 plus 1. So if you multiply this out, okay, you're going to Actually, let me leave this one out. It till you reach one. Okay, I don't know what is the biggest exponent will be. Okay. So from there, we conclude again by multiplying these. You're going to see this is what you get. All right, and it's not very hard to see that how we're going to get p minus 2 because multiplying, for example, this with this, it gives you p1 to the k1 minus and so on. All right. So this means that p1 plus 1 divides sigma of p1 k1. But now, with our assumption, since P1 is congruent to 3 mod 4, this implies that the following, that let's see in here, that P1 plus 1, this divides. Know that this divides, of course, sigma of P1, K1, and this divides, of course, sigma of n, because it's a factor here, which is equal to n. All right? Let's put these together and see what kind of a contradiction we get. Now let's substitute for, so let's take this one, P1 plus 1. The net result is this is going to divide 2n. Now P1 plus 1 is equal 4k plus 3 plus 1. And this is 4k plus 4. So we have from here, that 4k plus 4 divides 2n. And this in itself implies 2k plus 2 divides plus 1, sorry. Plus 1 divides n, and this is a contradiction because n is odd. So in other words, the will not be the correct form. All right. Now let's look at the K. So therefore, basically, P1 is not congruent to 3 mod 4. So it must be of the other type of primes mod 4, which is P1. All right. Now the second case is to show K1 is congruent, is not congruent to 3 mod 4. In other words, this would lead to a contradiction. All right. So in this case, again, let's look at sigma of P1, K1. And this is the sum of all these parts of P1 plus P sub 1 plus 1. Now, let's look at in here, when we are taking, assume it is of this form. So we're going to assume that K1 is congruent to 3 mod 4, which, and also remember that actually let me, no, this is not what I need. Since we have actually the piece, let's look at the form of the P sub 1. Now, since P1 is congruent, we already shown this, mod 4. This implies P1 is equal for m plus 1 for some m. Now let's look at this sigma of P1, K1, which I just say this is equal P1, K1. I'll write this statement one more time, plus P1 plus 1. I'm going to replace each one of these by the 4K, m plus 1 to the K1, plus 4K plus 1, K1 minus 1, and so on, up to for m. For m plus 1 plus 1. Now, let's look at each one of these. For m plus 1, I claim this is congruent to actually 1 mod 4, right? So in other words, when we take this as congruent 4, each one of the quantities inside the parentheses is going to be congruent to 1. 1 to the power k plus 1 plus this one is 1 plus 1. Now, how many ones in here? We have k1s. So this is k1 times 1 plus 1. And if we assume that if k1 is congruent to 3 mod 4, this implies that k1 is equal 4L plus 3. And again, this is mod, by the way, all of this is mod 4. Okay, all of this is taken mod 4. All right, now together with this makes this is equal 4L plus 4. And this is congruent to 0 mod 4. And we end up having the same contradiction that the 4 is going to divide. So from here, we have the 4 divide sigma of P1, K1, and this divides sigma of n, which is 2n, and it makes 2 divide set, a contradiction. All right. Nice proof, actually. You can see it's just kind of straightforward if you have an outline of what it is to be proved. All right, well, this takes care of section 11.3. I have 2 more sections to cover, and this is 12.1 on the Pythagorean triple. That will be a fun section. And then from chapter 13, we're going to do section 13.2. That is sums of squares, all right? Or which numbers can be represented as sum of 2 squares. All right, I'm going to stop right here.